I'm really excited and honored to be presenting today. My past and the present work on multi-material design for miniature robots. But before I start talking about the miniature robots, I would like to give you kind of what actually inspired me to build these miniature robots, and then how I kind of basically build up on that philosophy of small-scale animals. So first, one of those animals is ants. So ants is very abundant in the nature, and they can do incredible stuff collectively. So they can build bridges, they can build towers, even float like a boat, and also teach each other. For example, a more experienced ant can teach a less experienced ant how to find food, for example, for foraging. But little known about, so it's a lot known about their collective behaviors. But they are not only collective superorganisms. They can also have, they also possess incredible individual mechanisms. For example, have you seen a flying ant? Or this is not actually a kind of reverse video of an ant falling down. Have you seen a jumping ant? Navigating through cluttered forest environments. So these incredible creatures called trapjaw ants, they developed over the evolutionary process an incredible mechanism for coping with environment as well as escaping predators. So they use this miniature mechanism, the jaw, and use it for multifunctional purpose. So they just not only catch the prey, but they can also flip and then jump to escape predators. But also, they could use their legs, not only for crawling, but also using it for jumping in a cluttered environment. So these robots could inspire us to build more capable miniature robots. And these robots could be deployed in mass. And then they could start working together. They could navigate very cluttered, very difficult environment. They could communicate toward a common task. So even if some of them would fail, it wouldn't hinder them to accomplish the task. So it's really kind of a low-cost, mass-producible systems. But obviously, building these robots is challenging in terms of miniaturization, for example, embedding multifunctionality to their mechanical design, but also manufacturing them in mass. Let's look at the robot design across scales. So when we look at on my left side, on the macro scale, we could achieve an amazing kind of progress in developing robots that could be stationary, that could be on wheels, they could be flying around, thanks to the advancement in electromechanical actuation systems and modern manufacturing processes. When we look at the micro scale, and these robots were inspired by microorganisms, researchers have developed various methods for actuation and navigating, for example, bloodstream in human body or other organisms. For example, one day these robots could deliver some medicine to a certain part of the body. Notably, these robots have not self-contained actuation and mechanism. Everything is outside, so it's external actuation or excitation. It could be electromagnetic, it could be heat or laser pointing, and their mass manufacturing is thanks to the microfabrication process. So they could be really mass-produced in batches, like the silicon chip. When it comes to the mesoscale, again, we would face a challenge of miniaturization. For example, miniaturizing the conventional electric motors is difficult. And also, for example, manufacturing multiple components into a single small package would have another trade-off. So that would actually increase the complexity of the design as well as the size of the robot. And we would like to scale these robotic swarms, right? So we need to figure out how we can fabricate them in batches, just like the micro robots. And I call this problem a 3M problem. And throughout my PhD and here at Stanford, I'm trying to kind of address, scratch the surface of how I can address this 3M problem. Let's look at how robots were built and look at the state of the art. So for swarm robotics, we can see that these robots could be mass-produced thanks to their simple mechanical designs, but they have profound communication capabilities. And obviously, these robots were built to study complex swarm behaviors, but they were limited to 2D surfaces. So it could be a benefit to actually include more capabilities, or embed more capabilities that these robots could go to the 3D space. When it comes to the terrestrial multi-locomotion robots, so they are not only bound to the 2D surface, but they can now achieve 3D locomotion. We can see that they have complex designs. So they use conventional methods of transmission, actuation, and other mechanisms. For example, it could have a crawling. So they have separate mechanism paired locomotion. So you can have a crawling mechanism, which is separate from the jumping mechanism. And this would be hindering their miniaturization as well as mass manufacturing. Just imagine yourself putting together all of these small three-dimensional components in a meticulous manner, and then try to kind of scale it up to a larger swarm or collective like behavior. So if you look at the conventional methods, we can see that there is certainly some challenges. So if you like to, for example, design a simple joint, so we would have two kinematic pairs. So there would be pin and socket that would be moving relative to each other. But if you would like to motorize it, we would include a motor on the joint. Then further, if you like to have a high torque actuation of the link or the joint, we would introduce some gears, gearboxes to the motors. And then if you would like to, for example, generate a variable power actuators, we would include a spring, which we could load it and then generate variable power actuation. But also, if you like to have, for example, discontinuous power actuation, we would like to generate sudden power output from the mechanism. We would be kind of loading a spring, charging it, storing the potential energy, and then releasing it to convert it to kinetic energy. So which is very useful for jumping applications, for example. So we can see that the complexity actually increases when we include more functionality to the design. And also, number of components increases. So it could be that it's higher cost, more manufacturing and assembly time. But imagine you have a so-called smart material, or just a cantilever beam, let's say here in this example. Imagine that under no stimuli, it could be flexible, so it could act as a rotary joint. Then you would apply some stimuli. And this joint now start to move. It would have its embedded functionality. In order to generate high torque, you would just increase the size of the thickness of the cantilever, or you could play with the geometry of the system. And then, and then you could vary the stimuli to have the variable power output or variable torque output of the system. And you could also play with the bistable nature of these structures. So you could build a structure that could be bistable, and you could flip or kind of change between two states. Also, just imagine now you can have multiple layers of it built on top of each other, just like a printed circuit board. Then you can embed each functionality in a layer so that you don't have to assemble three-dimensional components. So that's how we built the Tribot. It's a multi-locomotion milli robot that can generate jumping, crawling, and walking. And these robots are inspired by trap giants. The mechanism in the middle actually is very similar to what trap giants have in their jaws. So it can open up its legs to 100 or about 180 degrees and snap through and close it quickly. The robot weighs about 10 grams and can fit on your palm. And maybe half of the weight in the surface of the robot is actually taken up by the batteries. So let's see how it works. We can do vertical jumps, so on any three of the edges, as well as we can, by changing the actuation sequence of these shape memory alloy actuators that I'm going to mention later, we can actually jump forward. We can also vary the power to get variable output from the locomotion mechanism, as well as we can overcome obstacles, for example, or even detect stairs. So we can embed sensors on board of this PCB body. And of course, we could also do some athletic behaviors. So why is it important to embed multi-locomotion for these small-scale animals? It's because if you look at the small-scale animals, as long as they shrink, everything around them environment becomes bigger and bigger. So they have to cope with this environment. And for example, they could crawl across a kind of flat, smooth surface. But then when they have an obstacle, they could jump over the obstacle. So that's what we would like to show here, is that we can transition from crawling to kind of flick-flack or rolling locomotion, and as well as jump over the obstacles. And making this simple and cheap robots is really, I think, beneficial if you could kind of mass produce them. And that could have very simple, let's say, electronics as well as sensing capabilities. But then with increasing the number, we could basically create tasks for each. And then they could work together instead of creating a one sophisticated robot, perhaps. And then here, for example, we showed the leader-follower scenario, where a leader robot here continues to scan the environment. So the follower doesn't scan it, so it doesn't spend too much energy on that. And the leader would just let the follower know that there is an obstacle coming soon, and then would jump over this gap. And the follower here would be computing how many steps it should crawl before it can come to the edge of this gap and then jump over it. So there is a lot of possibilities we could do with simple and kind of low-cost and mass-manufacturable robots. We could distribute the tasks. But this is how it's made. So it's very similar to how your iPhone or your Samsung device is manufactured. It's a layer-by-layer manufacturing process. But unlike these electronic components, devices, we embed mechanical functionality into the multi-layer process. So you can see here that we have the PCBs, some adhesive and the captain, for example, for the joint. And then we also embed shape memory alloy actuators that I'm going to discuss later. And by kind of sandwiching all of these components into so-called quasi-2D structure or sandwich, we can fold this sandwich to obtain the three-dimensional shape of the object. So basically addressing not only the structure, but also the functionality. You could embed multiple materials for different functionalities. And we studied the performance of the robot. So we could, I showed you that we could change the stimuli so that to obtain, for example, to generate different heights of jumping or the distance of. Or we also studied the robot's locomotion performance on a sloped or a flat terrain. So when we look at the cost of transport, so it's energetic cost of transport is a measure of how much energy is required for a robot to travel a certain distance. For especially the distance jumps, we can see that on the left, we see that there is terrestrial multi-locomotion insects, like the trapture jumping spider and desert locust. And we compared that with Tribot and other multi-locomotion robots. The Tribot could actually we have a comparable cost of transport, for example, close to desert locust or the jumping spider. But obviously the trapjaw ant here beats everyone. Obviously this data is for that particular time frame, but there are also robots now who could actually generate really high power at very small scale. And here's the evolution of the robot. So we started with the origin where we study like 3D printing methods as well as composite methods. And then we embedded some sensors to control the step size, the crawling step size, as well as the jumping height of the robot. Then we really embedded all that knowledge into kind of self-contained robot with end. And later we also studied the cage. For example, you notice that if the robot would fall on its edge on one of the sides, it wouldn't be able to continue its operation because it's just flat on the side. So this kind of elliptic cage helps it to self-right and then continue its motion. And later, before I left EPFL, I was involved in work where we were thinking about really, can we start from 2D and then it would self-fold and then self-write itself into 3D and then it would continue its operation. So this kind of 2D assembly process helps us to kind of maybe sandwich multiple of them and then kind of deploy. And this kind of flat robots could self-assemble and then start moving without kind of storing it in 3D. So the robotic origami allows us to embed a lot of kind of functionality and mechanisms. So here we show that this is the Tribot cage. Here we could also embed all of the components like the self-writing mechanism in 2D process. So you can be really creative about how you can generate these three-dimensional functionalities in 2D and then kind of manufacture everything in 2D and obtain that at the end. But we could also kind of have this cage foldable. So you could fold it, deploy, it would self-write, absorbing some shock, and then continue its operation. I touched on the fabrication process from the 2D components to the 3D structure of the robot. But what we really do in design space is we actually define a 3D robot and then all its a necessary component. And then we basically unfold it. We unfold it to the kind of 2D sandwich and then decompose it to multiple layers. And that's how the design process works. We try to kind of generalize or provide a kind of more systematic methods for this approach. So as I mentioned, there is a very important function of any origami is the geometry, and as well as the mechanisms that you would like to embed in the structure. And materials here is playing very important role. So we put these three components concurrently rather than sequentially because, for example, the shape of a smart actuator that can bend, for example, it plays a big role. For example, its geometry would be very much related to it because it's. I'll show you in a minute how the modeling or the behavior of these actuators are actually related to this geometry. Also, thermomechanical components and all of that together generate this mechanism. So it's kind of a fusion of the three components. That's why we put it in the concurrent process rather than like a sequential process. If you think about like let's say conventional robot design, you would be probably choosing, let's say, plastic, 3D printed plastic, or injection molded plastics, or CNC machined aluminum, for example. And that one is already defined by your manufacturing processes. They might come at the end of the design process, for example. But here we kind of also pay attention to the fabrication processes based on these three components. And in this process is really not definitive at the end. So we have to do some characterization, mechanical and material characterization at the end of this sandwich or the decomposed each component. and we have to refine this design process so that we could reach desired results. So at the end, I think like a concept or more like a paradigm, we could one day perhaps build this, make these methodologies into design tools. So we could really design, like we have Eagle for PCB design or KiCad, and we could manufacture them with embedded manufacturing processes, and then as well as test them, and then customize those designs according to those tests. So yeah, so that was for the design of these versatile robots. And I would like to talk about what actuation methods or actuators that actually made these robots possible to move and generate the functionality. So there are 4 types of actuators that I was studying. So one of them is a linear coil, and then bending sheet, and linear wave. So these 3 actuators were shape memory alloy or nickel titanium alloy, which you could basically form them into, let's say, a coil, and then anneal it or heat it at high temperatures. And that alloy would memorize that shape. So once you kind of stretch it, and then you apply heat or you pass a current through it, which is called Joule heating, that would be compressing again kind of to the memorized shape. So you can do this cyclic kind of extension and compression of the actuator to be used for robots, for example, like an artificial muscle. So how we actually use the shape memory alloy actuators, the coil in this case. So for example, if you like to have this crawling motion, we just need a smooth, continuous kind of operation. So it's like going back and forth, right? So for that, we needed 3 coils, and then we could activate one at the bottom to close the leg, and then activate the ones on the side to open the leg. So we can basically control it continuously smoothly. But in order to generate this sudden snap-through mechanism, we could still use the same approach here. So we can open the legs of the robot to 180 or more degrees, and then we could start activating the bottom one. So that activation creates actually compression at the middle joint. So at some point, the mechanism is looking for a stability point. So it snaps through to the other direction, generating a high torque, and that torque is translated to ground reaction force that lifts the robot up. It's worth mentioning here is that you can see here that this shape memory alloy spring behavior is quite similar to the steel spring, for example, which behaves according to Hooke's law. But one difference here is that the shear modulus here is a function of temperature. So because it's a thermally activated actuator, the temperature will define how stiff this spring would behave. And then we embedded some sensors on board, and we used this actuator. And then here, I show here is that we can basically modify the power. We could modulate the input power to generate different jumping heights. And these springs are actually very kind of tedious to manufacture. You have to coil them up and also kind of go through that process. So in order to avoid that, we were thinking, can we actually have a layer of the sheet and use it for that purpose? So, but that would be a kind of a bending rather than like a linear compression motion. So, but the challenge, let's say, with this kind of bending sheet type of actuator is that you wouldn't be able to heat it like the coil. It has a higher resistance, electrical resistance. So in order to kind of reduce that, we implement like another layer of heater, which would not directly hit it, but conduct the heat to the actuator. Again, it's very similar to bending sheet equations. So where the elastic modulus is now as a function of the temperature, and the temperature could be, and that elastic modulus temperature is a function of called Martin-Cziczek fraction coefficient. I will not go to the details of the equations, but basically their behavior could be nonlinear. Let's say it could be kind of cosine or sine function. It could be exponential. So different literature kind of put it in a different and tried it in different methods. In here we can clearly see that our behavior for the actuator is quite kind of a cosine or sine function. And we embedded these actuators for let's say like a flat sheet of material that could self-fold, and then not only self-fold could be controlled, and also kind of transition to other states. This one is going from flat to U-shape, from U-shape to, let's say, tetrahedral shape. All right, so I mentioned about the coils, which are difficult to manufacture, and maybe a sheet would be easier to manufacture, but the sheet cannot store potential energy. So we would need certainly something that could be kind of coil-like, which could store energy, more elastic, unlike sheet. So we combined both properties in a flat sheet type of wave SMA actuator. So the fabrication process is very easy. So you could have a sheet of material, and then you could score this serpentine structure on top onto the nitinol sheet, cut out using the laser, and then not only you could create these kind of stretchable elements, but you could also stack them. So you could create high force actuators as well by just kind of using adhesive and other methods. And we use these actuators for the case of reconfigurable grippers. So what does it do? So the reconfigurable gripper is a suction gripper. And as you know, the suction gripper in the industry have fixed shapes. So the amount of, or the shape of the objects they can pick up are really, really limited to their shape. But we were thinking, can we actually have reconfigurable version or shape-morphing version of this robot? So we, again, used origami design methods. So you can see here in the mod 1, it has a larger aperture, and then it could change its aperture accordingly by selectively activating embedded shape memory alloy actuators. And the manufacturing process is very simple here, that we have some silicon where we integrating more rigid components like fiberglass, and then we embed actuators. So it becomes a kind of a single piece of material. And then here, please note that in the inside of them, we use coil, steel coil type of actuators. But the actuators from the outside are wave type of actuators. As you can see here is that, for example, picking up a very narrow and long object like the pen, here is quite difficult. So we can switch to a different mode. And it's really, if you like to represent different, like so many different geometries of these apertures and then objects that you want to pick up, you can really play with origami structures and then how these structures could generate those shapes. Yeah. And this actuator that I want to present is quite kind of different from the shape memory alloys, but it has benefits. So this is based on fluidics, so it's pneumatic. One of the challenges of the shape memory alloy actuators is their speed or the bandwidth. They're quite slow. But pneumatics, we know that it can be quite fast. So, and we were thinking, all right, can we design different types of robots, but could also be behaving or reconfiguring to different shapes really fast? And that's how we come up with the idea of kind of embedded fluidic chambers. So what it does is you could embed fluidic channels, for example, in this Miura origami pattern. You can see there is mountain and valley folds, and then you can design those folds to have some fluidic chambers. If you suck the air out from these chambers, some of them would be collapsing, and this collapse would generate some folds. So that's the basic idea of the structure. So as you can see here, by having a single port, you can distribute all of that actuation onto the 2D surface. And you can design it to be mountain or valley. You could also design it to be having different moment or torque generated at their folds. What we also noticed that by changing for example, by altering the fluidic chambers or the cross-section area of the fluidic channels, you could also have certain delay in certain actuation response. So we used that delay actually to generate kind of sequential folding behavior with these structures. Yeah, that's pretty much summarized that multi-layer, multi-material processes really could speed up and enable us to have kind of mass-producible, multifunctional robot. And next, I would like to actually touch on the next application, which I'm actually involved here at Stanford. It was very exciting for me to see different challenges in different robotic fields where this kind of approach could be applied. So as you know, haptic interfaces could enable us to interact with the digital environment. It could be a virtual world, a metaverse, or any other definition of the system. So in this three-dimensional virtual world, we would like to have compelling, realistic, intuitive interaction behaviors. So in order to be touching something, you should, for example, when you interact with the physical world, for example, touching this bottle, when you pick it up, you basically would feel what's the weight of the object. For example, there are multiple sensors in your body. One of them is mechanoreceptors that tell you how heavy is this object. And one of them is like, for example, you would feel the friction. Another thing, for example, does the bottle rotate in your hand? You could also kind of feel it by rotational friction, or you could also feel how soft is the bottle. So all of that multimodal information is processed in your brain, but picked up by the mechanoreceptors. So these mechanoreceptors provide kind of information on different attributes of the object. It could be texture, it could be rigidity, it could be weight, and so on. And the haptic devices that were developed for these cases is mostly, for example, for a fingertip, which is the most sensitive area of our hand for touch. And these fingertip devices could generate different degrees of freedom of motion. So degrees of freedom, basically, you could imagine that it is like how complex attributes of the object we could recreate, or how complex it could be the interaction behavior. So, for example, if you go from left to right, you see that the 3 degrees of freedom we have the 3 degrees of freedom kind of haptic devices that were inspired by conventional Panto or parallel robot systems in the industry, and then kind of basically trying to miniaturize them into a small footprint. But we also see that we have 4 degrees of freedom using some origami, but using, again, some conventional actuation methods. So really, for me, was, again, coming back to the 3M problem. Can we actually address it using the same methods that I was presenting earlier? And that's how I started working the FingerPrint. So FingerPrint is a fully 3D printed haptic device. So it requires 0 assembly process and embeds 4 degrees of freedom capability. So it can stretch your skin, it can provide pressure or vibrations, and it's really monolithic. So you can design it in one piece, print it in one piece, and then by kind of cleaning, post-processing of this 3D printed piece, you could have it ready for your application. So how it works? You have a single piece of material with embedded actuators readily in the system, some fluidic channels, and also the mechanism is, again, uses some origami that I'm going to show you later. So this tactor interacts with your fingertip, giving you 4 degrees of freedom interaction and stimulation. You can change the frequency of the stimuli so that you can have, for example, vibration. You could also have faster interaction. Our interaction is not really kind of at the same bandwidth. So we have a kind of varying frequencies when we interact. So it could be, for example, for finer objects that you want to know the texture about. It could be higher frequencies, or more coarse objects would have lower frequencies, and so on. Yeah. So the main thing in the body of the fingerprint is this origami mechanism, or water bomb-based mechanism. It has 8 foldable actuators, and these foldable actuators are basically, again, like chambers, but now 3D printed. And by applying some vacuum to these chambers and selectively through these fluidic channels, we can make this tactor in the middle move in the desired direction. And here is the origami mechanism. It's a water bomb base. This mechanism can generate 3 degrees of freedom. So by, for example, if you change the angle of the folds here, on the creases, you can generate different motion on the tactor. So, but since our device is pretty soft, when we actuate all of these folds together, it compresses and generates the pressure. And that's how we achieve the 4 degrees of freedom, which is not defined by this origami mechanism. And yeah, it's really easy to kind of mass produce or scale it in a single printing process. And some of the key considerations, obviously, is to think about how you would design the supports. Where would you like to install them? Because this is a soft material, and we are using very thin layers of for example, the actuator walls. So we would like to kind of have a right amount of, let's say, support, but also we would want to be able to remove them later after the post-processing, so that it's not very laborious procedure. Yeah, and I think key takeaways from here is really that we could change the vacuum pressure to actually control the force output of this tactor. For example, here we can see that the tactor can move and kind of generate different forces, for example, for the pressure, Z force, by just changing the input fluidic pressure. So it gives us another dimension where we could do maybe closed loop control. And I further extended this method to wrist-worn device. So unlike like the fingertip device, wrist-worn device allows you to kind of place more components, or generate kind of display-like capability on the wrist, because there's so much real estate on the wrist rather than on the fingertip. So this device can generate about 20 newtons of force, which is quite high. And again, here we use a little slightly different method. So we use bellow type of actuators that can compress when you apply vacuum. And by selectively activating these bellows, the tactor in the middle here can generate different motions. And I can show you this motion here. Sorry. So the tactor here generates, by playing, so by kind of activating these actuators in different manner, this tactor can be, for example, applying shear in X direction, Y, or it could even apply like a twist motion, or stretch your skin, or as well as squeeze. So by scaling up this number of Hoxels, for example, on your skin, you could generate like a display-like haptic interaction. Yeah, so we're currently studying this fingerprint on the phalange, for example, which is called the haptic relocation. One of the challenges with having it on the fingertip is really the physical interaction between fingers when you're trying to grasp small virtual objects. For example, in order to, we are currently using these devices to be relocated to the, as a ring, for example, and use that to understand how people perceive or how effective it is on the phalange, for example. And also we are generating this kind of modular displays with these Hoxels, where we could kind of put them not only like in one direction, but we could put in the opposite. We could scale them, so many of them on the skin, and then have more input. Yeah, and other projects, as Mark mentioned, I work with Crystal on this fluid-actuated 4 degrees of freedom origami mechanism, which can be fabricated in 2D, and you basically obtain the 3-dimensional shape of the robot, and also like a twisted string type of actuation. So here we also study like 3D printing with more rigid materials, and then we use it for its compliance to control its motion. Yeah, with that, I would like to thank all of my collaborators and colleagues from EPFL, as well as at Stanford. And yeah, moving forward, I think we could build this mesoscale or miniature robots that could be interacting with your body, with the environment, or with themselves. And we could also generate so much capability with these designs. Yeah, thank you so much.
While people think about it, I'll ask a question while other people think about it. So one of the things that's sort of always interested and maybe concerned me a little bit about the origami robotics going to smaller scales is that we don't get perfect hinge joints. We have flexures, and the smaller we get, the more true that is. Yes. And what should we, is there something we can do about that, or do we just live with it and live with the fact that there will be this more complicated motion with side effects?
Mm-hmm. Yeah, that's a great question. Yeah, I think the form factor and scaling really plays a role here. Obviously, like micromechanical systems field, they use a lot of these flexure type of joints because it's much easier to manufacture them at that scale. But mesoscale, I would say they're good enough, but not really like perfect as pin and socket joints. They deform, but some of the, let's say, results, they show the characterization and kind of quite good results. But I think, yeah, we have to be careful about, like, it really depends on the let's say the gap size of the hinges or the structure of the material itself, which I mentioned earlier. So yeah, so I think there is some potential there where we don't need high precision applications. For example, haptics could be one of them because the human perception is not that accurate. Let's say to precisely feel 50 micron versus 100 micron, or even, I think, millimeters. So it's really, I think, important to define the scale and kind of application scenario for them. Yeah, I think there's one question there.
All right, I'll get, since he was a little bit faster.
All right, so one kind of general question from the Zoom is, what got you interested in making these types of robots in the first place?
Well, yeah. I think the overall idea, let's say, of materials, for example. I previously, in my master's, I was working with piezoelectric actuators. Mm-hmm. That was the starting point, I think, when I was kind of very much excited about material field as well, and kind of including in my expertise. So, and origami and the design itself really excites me. So combining all of them was really something that I wanted to work on. And yeah, that's how I started my journey at EPFL. Yeah.
Great, thank you.
Okay, there's two. Thank you first and you're second.
Oh, how much does 3D printing one origami cost?
Cost?
Yeah.
The 3D printed haptic device?
Yeah.
It's a great question. I haven't calculated it. I don't have the precise number. But given, I think it's a commercially available 3D printer, which costs $3,500, which is not very expensive, I would say. Like many people use it. And it's very precise, 50 micron accuracy.
Which printer is it?
It's Formlabs. Formlabs, and I use their available cartridge, which is $200 per cartridge per tank. Even not per tank, like cartridge. And that lasts me to print, I don't know, hundreds of pieces, right? So it's a 200, 400, so maybe dollars, a few dollars. Yeah.
Are there any like specific applications you were keeping in mind when designing the FingerPrint?
Yeah. Yeah, that's a great question, yeah. So one application is really like have three-dimensional mouse, right, or keyboard in virtual environment. So when we have the headset, everything visual is three-dimensional, and our interaction should be accordingly kind of more intuitive. So that one way is like having a device in your hand, a headset, and then you would be kind of touching the environment, let's say clicking the button. So clicking the button even like needs to be done properly, right? So there is a recoiling of the spring that you do, and then the texture, or for example, if it is hot, if it is cold surface. So all of that potentially should be included in this device. So I mean, in reality, you would be touching the space, the air, right? But that would give you a feeling if you are touching the real object. Yeah, so that's one of them. And another thing I think is skill transfer and then education. So for example, you could, surgeons could do thousands of these training hours in virtual environment without dealing with real objects or real tools. So that would give them a lot of possibilities to learn.
I can project, that's okay.
Yeah, but I think SCPD wants to record it.
I'm always curious when researchers pull up images of ants and stuff like that. Like where do people benchmark all these insects and organisms? Where do people find all these small details of their anatomy and use that for inspiration? Is there just some university that's done some papers about that, and that's what people just build off of, or
Yeah, that's a great question. I'm not a biologist, or I am. What I did was I saw a video posted, and it was about a paper which some biologists were studying their behavior, and I went and then found so many papers actually in biology, and I started to reading about them. So that's how I think it's usually done. Is there is a lot of done by researchers, and you could kind of build on top of that. I think, yeah, that was my experience at least. Just to add, and I also kind of reached out to some biologists, and we also discussed like how they usually work, and because they were like experts in that field.
Thank you for the presentation. I was just wondering if you see potential applications for macro scale versions of the trap jaw robots or any of the robots we talked about. I mean, for haptic devices, I think it's kind of clear that we want it to be advancing, let's say, the training process. We want it to be used maybe in the next generation of digital interaction. For, I don't know, consumer devices, or it could be for more specific training and skill transfer. For I mean, so there is like multiple things. So one is to, for Trap-Joanne type of robots, for example, one way is to have these artificial capabilities is to really maybe understand these natural systems as well, how they behave. So it's kind of, but also like if we emulate those systems, we could have in the future potential like for interplanetary exploration. Like we could deploy them in mass and then really not be dependent on single sophisticated multi-billion-dollar machine. Maybe that could be the future of it.
We're near the end. If there's time, we can do one last if there is one. Otherwise, I'll close it. And thank you. Oh, one more. Okay.
I'm just curious about the plot. It was kind of near the beginning, just about the mass and energy usage of each. So what are the fundamental constraints? Because it looked like there's still a big gap between what ants can do and what we can do with robots. What are the fundamental constraints preventing us to get down to the mass levels of the ants?
Yeah, I think that's a great question, and I was always asking me this question, right? I think it's artificially recreating the structures. Probably we could recreate the structure, but like muscles. And all of that is really so difficult to recreate with artificial means. So, I mean, ideally we would have this muscle, right? But then is it, we have to put it into, let's say, more moisture environment and so on. So there are researchers who are actually working on kind of taking this muscle and be used for these kind of cases. But again, there's so many challenges of like keeping those muscles alive, like keeping them moisturized yeah. So, but as you saw like in macro world, we generated these electromechanical hydraulic actuator methods, which are quite effective and could be much more powerful than elephant or whale, right? But again, it's the same thing. Can we do more with artificial rather than like replicating exactly?
Thanks very much.